Just a quick question. How come theta for tension was 55 degrees?
Because the problem gives us a 35-degree angle at the top of this triangle.
Okay.
And then, you know, this is making the right triangle, so the angle at the bottom must be 90 minus 35.
Okay.
Right? And I just realized that the beginning of this problem wasn't recorded, so I'm recording now. I will add a little video in between, so where I'll go back over this first part for if you want to look at this again later, or if you're tuning in only online after the fact. So apologies about that. Any other questions about the first part of this problem, finding tension? Okay, so the second part is to find the force from the hinge. And let's see if they want magnitude and direction or components. Think, it says the force. So I think normally if I see force, I'm thinking magnitude and direction. So we now do sum of the forces in the x direction equals 0. Sum of the forces in the y direction equals 0. We could, by the way, use another torque formula if we wanted to find, well, if we go back and look, we would be able to find the y component of this force, but not the x component, because the x component, you know, how would I do it? I would pick a pivot point on the other side, and the x component wouldn't produce a torque, but the y component would. That's not easy. It's I don't want to even show you how to do that because it's much longer than this, but it's possible to do it that way. So in the x direction, we just have F hinge x minus Tx equals 0. So going back and looking at our picture, only the force hinge and the tension have x components. And then in the y direction, all four have y components. So we have F hinge y plus Ty minus force of gravity minus u equals 0. So the F hinge x is just T times the cosine of 55, that angle that we found at the bottom here is 55. And F hinge y is going to be force of gravity plus W minus Ty, which is T sine of 55. So we put in our numbers, 1945 times the cosine of 55. And over here, we're going to have 500 plus 700 plus 1945 times the sine of 55. So the FHX is 1,116 newtons, and for the Y component, it's 2,793 newtons. So this means this force, Cat?
Is there supposed to be a plus sign or a minus sign in front of the FHY?
There should be a minus sign. Thank you. And then that's going to change this number, right? Yeah. Okay. Sorry about that. Thank you very much. So 1,200 minus 1945 times the sine of 55 is minus 393 newtons. Okay. So that means that the way we drew the force in the beginning was a little bit wrong. The y component should have been negative, and not that big, so maybe something like this. So to find the angle, we would do the, the tangent of the theta would be minus 393 over 1,116, and so theta hinge would be the inverse tangent of the y component over the x component. This is minus 19.4 degrees. That looks like it fits with having a positive x component and a negative y component. So I think I don't have to add 180. And the force hinge, the magnitude of this would be the magnitude of the square root of the sum of the squares of the components. That is 1,183 newtons. Okay, so finding the sort of the last force, whatever force you have left, usually is simplest just to use net force in the x direction and net force in the y direction. And by now, you're all seasoned veterans at that process. So any questions about the second part of the problem? Okay, yes, Haley.
Why, when we're finding the force of the hinge, are we taking the square root?
What we're doing is the Pythagorean theorem. So, a squared plus b squared equals c squared, right? So to find the c, you take the square root, that kind of thing.
Yeah, okay, thank you.
Does that make sense? Okay. All right, so next problem I wanted to look at was 10.27. And so in this case, we have a person who is holding a 20 Newton weight. Okay, so you've got someone with holding something in their hands, right? They've got a big object in their hands. And it's a 20, so let's say the force of gravity, or no, let's call it the weight, is 20 newtons. So that's only about 2 kilograms. That's a very light weight. And they say the lower arm weighs 65 newtons with the center of gravity as shown. So they're giving us a center of gravity that is off-center and saying that the force of gravity acting on the arm is 65 newtons. So, what's happening in here inside the arm is you have the radius and ulna, and the biceps connects, gosh, I think it's to the ulna, I don't remember, nurses help me out. Whichever one is on the inside, the biceps connects there, and then there's a joint where the upper arm connects to your elbow. And so in terms of forces, they're telling us that the distance between the force of gravity and the elbow is a total of 10 centimeters, while the length of the whole arm here is 35 centimeters from the elbow to the center of the hand. And they're giving us some information about forces. They say that the biceps is pulling upward at an angle, like that. And we know force of gravity is downward, and there's also a weight here. Call that the force biceps. And what they don't really tell you is that there's another force here, probably must be kind of more like that, from the upper arm on the elbow. Okay, so those are the four forces. And what we're being asked is what is the tension in the muscle, or the force that your biceps has to exert in order for you to just hold a 20 Newton weight. They give us another distance of 3.5 centimeters. Okay, so that's the picture. And what we want to do is we want to choose a pivot point. And again, the natural pivot point of the elbow is also sort of the smart pivot point to choose, because we don't really know what the force on the elbow looks like. So we're going to call that our pivot point. And when we do that, we can draw in R values. So there's going to be one R value here, which we could call that the, R for tension. And then we're going to have a separate R value that comes along here, which we can call that RG, from the elbow to where the center of gravity of the arm is. And finally, we're going to have one more that comes along like that. Now, it doesn't matter really that I drew the weight a little bit higher than this axis. And I'll maybe at the end of this, I'll talk about why it doesn't really matter so much. But for now, that's just a little bit of sloppy drawing on my part. And the R for the W is from the elbow all the way there. Now, they gave us an angle additionally. They said this is a 20-degree angle up here, which means we have a 70-degree angle between the biceps muscle and the whichever radius or ulna that it's connected to. So that's our picture. And we can now write down net torque equals 0, where we have a torque from the elbow, a torque from the biceps, a torque from the force of gravity acting on the arm, and a torque from the weight in your hand. But we are going to cross out the torque from the elbow, and then the torque from the biceps, that's trying to bring things counterclockwise, and the other two are going clockwise. So now we have torque from the biceps equals torque from gravity plus torque from the weight. And that's R biceps, force biceps, sine of theta B, that's equal to RG, FG, sine of theta G, plus RW times just W, sine of theta W. Okay, so this is, you can see, this is basically the same exact math that we've been doing all along. So the force biceps will be equal to RG, FG, sine of theta G, plus RWW, sine of theta W. All of that over R biceps, sine of theta biceps. So I'm going to clear things out on the top here a little bit, just to make my table. And our table should have 8 entries: 1, 2, 3, 4, 5, 6, 7, 8. So we have RG, FG, theta G, RW, W, theta W, RB, and theta B. We just want to fill in all of these things. The RG, looking at the picture, is 10 centimeters. Force of gravity, 65 newtons. Theta gravity, 90 degrees. RW, 35 centimeters. W is 20 newtons, just given in the problem. Theta W, also 90 degrees. Again, like I said, my picture is a little bit funny. I'll explain why it doesn't matter later. Our biceps is given as 3.5 centimeters, and the theta biceps, according to the picture, is 70 degrees. So we can work all of those numbers in. Now, you might be wondering, do I need to convert the R's into meters? The answer is I do not, because we're going to be dividing R's by R. So if I have centimeters on top and centimeters on bottom, the centimeters cancel out. So you could convert to meters, but it's not necessary. So our gravity R is 10, and then we have times 65 times sine of 90. Sine of 90 is just 1. So if I know that ahead of time, it might be easier for me to just kind of put those in as 1. RW is 35, and then times 20, and then times 1. That sine of 90 is going to be 1. And on the bottom, we have our biceps, which is 3.5 times the sine of 70. Let's see what we get. I get 410 newtons. Okay. So let's just think of
I think he disconnected.
which would be about 92 pounds. So to lift a 4.4 pound weight, your biceps has to exert almost 100 pounds. Ziad.
Professor, I kind of missed most of what you said because on my side at least it said that you disconnected.
On your side, it did what?
It said that you disconnected.
It said I disconnected?
Yeah.
What was the last thing that I did or said?
If I remember, we were right at 410 for the newtons. for
Okay. So did everybody else have the same experience? Raise your hand if you lost me for a little while. Okay. Thank you. So here's what I'm saying. This force is 410 newtons. That's the force your biceps has to exert in order for you to lift 20 newtons. That is a huge discrepancy. Now, to put it into kind of terms that makes more sense, because you're not used to newtons probably any more than I am, 20 newtons is about 2 kilograms, which is about 4.4 pounds. So in order to lift 4.4 pounds, this force would be equivalent, I just did a little conversion when you lost me, to 92 pounds, almost 100 pounds. So to lift, let's say 5 pounds, your biceps has to exert a force of 100 pounds. Now, you can lift a lot more than 5 pounds. So that's a ratio of about 20 to 1. So if you were to lift, let's say 20 pounds, 25 pounds with your biceps, doing an arm curl with 25 pounds, your biceps muscle is exerting 500 pounds of force, at least for this person. This person with the length of arm they have and the geometry of their arm. They would have to be exerting a 500-pound force in their biceps in order to exert only a 25-pound force, or to lift a 25-pound weight. So that means that our body is operating at an extreme mechanical disadvantage. And what I said, maybe when you lost me, was that I thought that this would be very interesting and important to those of you who are interested in the human body, because our body is operating at a huge mechanical disadvantage. Our muscles are tremendously stronger inside than the forces that we exert on the outside of our body. Just think about it this way. If your biceps, if you can just hold 25 pounds in your hand, then that means your biceps is exerting something like a 500-pound force. If we could exert that 500-pound force on the outside, think how strong we would be. If that biceps muscle were connected at our wrist instead, so that biceps force of 500 newtons or 410 newtons, 500 pounds, could be attached at our wrist, then you would essentially be able to just lift up the back end of a car without too much problem. And I'm guessing most of you cannot lift up the back end of a car without too much problem. But you would be able to do it. Our muscles are strong enough, but our geometry is sort of making us at a disadvantage. So anyone have an idea why we are operating at such a disadvantage? Good. So I'm going to offer you extra credit to think about this for a while. I'll post it on Blackboard, but this is, you pretty much, it doesn't matter what you say, you're going to get the extra credit if you just think about this and come up with what you think is the answer. I don't know that there's one answer or even an easy answer to this question, but the question is, why are we designed or constructed in such a way, that we have such a big mechanical disadvantage? There must be some benefit, or some trade-off. But obviously, it would be nice if we could be, if instead of lifting, using a 500-pound force inside my arm to lift a 25-pound weight, if I could just lift a 500-pound weight, I would be very happy with that. So why are we not constructed that way? What's the benefit to being weak, or the trade-off? What advantage do we gain by having this disadvantage? There must be something. Whatever, however you think of it, there has to be a reason why we are constructed this way. So that's the extra credit. It's a very open-ended question. It's not a try to Google the answer, why are our biceps not attached at our wrist? I don't think you'll find anything if you Google that. It's just really more for you to think about, what do you think, and basically write a thoughtful couple paragraphs of, and depending if you're really into medicine, medical science, that kind of thing, then you should think about this even more. If you want to be a physical therapist, even more. Think about all of the ins and outs of this. It's a really interesting question. Okay, so any questions about what the extra credit is? All right. So so that's how it works. You can see that even though the picture's totally different, the geometry is different, it's a totally different scenario. Once we get those forces in and we write out net torque equals 0, that the procedure is virtually identical. Okay, we're doing essentially the same thing over and over. So I want to do one more problem like this and then just set you free to do your own homework. So the next problem is 10.28. So this is a problem of a woman lifting a bowling ball. So, I don't know if I can really draw this, especially with the lag that I'm having. So here she is, she's kind of bent over and she's holding this bowling ball, and, she looks more like she's a reindeer or something. But anyway, this is a woman, and she's a happy woman, or she's a rabbit. I don't know. Someone lifting something. And it says she's lifting a 60-pound bowling ball. So we have a weight. Let me maybe change colors. And weight is 60 newtons. We want to find the tension in her back muscle and the compression force on her spine when her back is horizontal. Oh, sorry, I just remembered. I wanted to go back and talk about why it doesn't matter exactly how I drew the picture here. So before we get into this problem, let me just give you a real quick little aside. So here's my pivot point. And I have an object, and there's a force here, W. And we're going to draw in an R. There's R. And I drew it in this time as if the force is making a perfect right angle with R. But in that last picture, what we had was W was here, and if we go back and look at it, it's a little bit above the axis, and so the R technically R should have been like that. Okay, that would technically be how it's supposed to look. And the torque, there would be some kind of angle here that's not 90 degrees. But remember that torque is R times F times sine of theta. And when we first developed that, I said that we're looking for the component of the force that's at a right angle to R, but it would be just as good for us to put F times R sine of theta, which means it's the force times a piece of R that's perpendicular to the force. If we look at this picture, R times the sine of theta, if we make a right triangle out of R, okay, then this side here would be R times the sine of theta. And that is exactly the same as the length of the R that you get if you just take the work and you move it down so that it's perpendicular to that. So the idea is when I have an R, that's up at an angle and a force like that, it's just as good for me to take this force and move it down come on okay, and move it down and let R be just the kind of perpendicular distance. That would give me mathematically the same thing as if I have my force up here and R over here as having my force moving it down and making a right angle and having a shorter R. So essentially, I'm not sure if that's making any sense at all, but when I have something that looks like it's not really making right angles, I'm allowed to just move this force down a little bit and make a right angle. And mathematically, that's going to be exactly the same. So if I don't have angles clearly given in my picture, then I just want to kind of put all of my forces on sort of on a line that so that they're making right angles with that line, if possible. Any questions about that? Did that make any sense at all? Like 10% sense? 20%? Okay, well, you might see that idea in some problems. And anyway, if you get stuck and you feel like you're having trouble with that, let me know, and I'll see if I can maybe explain it in a different way. So back to this problem with the rabbit trying to lift up the bowling ball. So they say use the approximate the situation as shown in the diagram. So they give us some forces, they and distances. They give us a horizontal axis. So they're basically making that same kind of approximation that I was making, and they're saying the force. So this is all problem setup. This is not something we figure out. The problem's giving us it. They say there's a force of gravity just from the weight of the woman, her torso there, and then the weight, the W is there. So maybe the weight of the woman's back is a little bit longer. So I'm just going to make that longer. And then at her hip, there's going to be a force that they call the horizontal force, and then the vertical, sorry, that should be up, the vertical force. So this is the setup. So we have the force of gravity and the weight and a force vertical and a force horizontal that are the forces sort of at the hip joint. Okay, so we're approximating her when if she bends over and makes a right angle to pick this thing up, and we're trying to find out, essentially about the strain on her hip. So it tells us that her upper body weight is 250 newtons. And we have the 60 Newton weight there. And we want to find FV and FH. So first of all, to find FV, we could just sum the forces in the Y direction. Oh, hold on, there's one more. I'm missing one force, which is the back muscle, the key force here. So they're giving us essentially a tension in the back muscle. So we want to find the strain on the hips and on the back muscle. So we're going to pick a pivot point, and I would recommend this joint as our pivot because not only can we eliminate sort of two forces, we don't know what those forces are. The problem gives us a 12-degree angle for the back. And now we can write out our net torque equals 0. So we're going to have torque W, torque tension, torque G, torque V, and torque H. But we know because of our choice of pivot that those two can cancel out. And furthermore, the torque from the tension is trying to bring things clockwise, so it gets a minus sign. The other two get plus signs. Now, I didn't draw in my R's yet, so let's, normally I've been doing that a little earlier, but it doesn't actually matter much the order that that step comes in. So we're going to have an RG, and we're going to have an RT, and finally there's going to be an RW. I'm just drawing it offset a little bit because it's easier to see if they're not laying on top of each other. And we are told some lengths in the picture. If that's the total length from the hip to the arms, then the back muscle is acting at 2/3 of the length, and the force of gravity, sorry, that should have been the back muscle, and then to the force of gravity, that's L/2. So those are my 3 lengths. Okay, I want to solve for the tension, so I'm going to move that to the other side, and we get torque tension equals torque W plus torque G. Now this all of a sudden, equation-wise, this looks pretty identical to our previous problems. So torque tension would be R tension, tension sine of theta tension, and torque W is going to be RW W sine of theta W, and then we have RG FG sine of theta G. And to solve for the tension, RW sine of theta W plus RG FG sine of theta G, all of that over RT times the sine of theta T. So we can make a little table where we put in RW, W, theta W, RG, FG, theta G, RT, and theta T, and now we just fill them in. So the RW is the full length. Let's do the R's first. RW is full length, RG is L/2, and RT is 2/3 L. The W is 60 newtons. The force of gravity is 250 newtons. And my angles, we have a theta W, which is 90 degrees, and a theta G, which is 90 degrees, but a theta T, which is only 12 degrees. So I copy this to the next page. We can fill it in. Should copy my table too. Okay, so there's my table. So we're going to have L times 60. These guys, because they're sine of 90, they both give you 1. So I'll just use that now. And we have L over 2 times 250, and all of that is over 2/3 L times sine of 12. So the R's, the L's, that is, cancel out. And we're then getting 60 plus 100, or 1/2 times 250 is 125 newtons. And that's divided by 2/3 times the sine of 12. You don't have to write that step out if you are good with your calculator. And I get 1,334 newtons for the tension. And so you can see again, this is a lot of strain on your back to lift a 60 Newton weight. And the strain in this case is largely coming out of this angle. Okay, so because that angle is so small, when we divide by a small number, we get a really big number. Okay, so again, from a perspective of injuries, you can see why you don't really want to just lift something with your back muscles. Now, to find the forces on the hip, we go back into our picture and we sum the forces in the X and the Y direction. So in the X direction, we're going to have Tx minus the horizontal force equals 0. And in the Y direction, we're going to have Ty plus vertical force minus Fg and minus W equals 0. So the Fh, that is the horizontal force, is just equal to T times the cosine of 12. That's my X component. That's 1334 cosine of 12. That's 1,305 newtons. And to find the force vertical, that's going to be Fg plus W minus T sine of 12. So that's 250 plus 60 minus 1334 sine of 12. Okay, so I get about 33 newtons. Okay, so, and I don't know if we want to find the compression force on the spine, so we want to find the magnitude of this thing. So that magnitude would be the square root 1305 squared plus 33 squared. Which is still about 1,305. Okay, so the back muscle has to exert a force of 1,334 newtons. The compression force on the spine is also around 1,300 newtons. If you want to know in terms of pounds, that is yeah, that's like around 300 pounds. Okay, so you can clearly see how you can get injuries in this way. All right, any questions? All right, so you have maybe 4 more homework problems tonight to do on this. Now, I noticed that the last 2 problems that I assigned, so almost always the problems I assign, I have the 11th edition of college physics. They're the same as in the 12th edition, but the last 2 problems, they are in the supplemental or supplementary problem section. And so the problem numbers may not be right if you have 12th edition. So after class, I'm going to take a picture of these 2 problems and upload them on Blackboard so you can make sure you're doing the right problems. And when you see them, you'll be able to match. They're still in your book, but they're going to have different problem numbers in your book. So just keep an eye out for that later this afternoon. I'll post an announcement when I have that picture uploaded to Blackboard. But it's the last 2 problems for tonight's homework. And once you complete all of this homework on torque, then you should be ready for the contest. So tomorrow we are going to go back into that table of translating from Latin into Greek and start talking about some other topics within that framework. But those topics will not be on your upcoming contest. All right, any questions? Okay, so as always, if you have a few questions, you can stick around, but otherwise I'll see you tomorrow. Thanks a lot.